Now the third type of rebar which I would like to talk about is the TMT, or quenched and self-tempered QST steel bars. Okay, and this is a bar which is widely used in today's market. So it's very important for you to understand in detail about this type of rebar. Okay, so we will focus a little bit more on what are the important quality parameters, etc., for this type of bar. Now, how is it made first? So these bars, you can see here 100 degree Celsius temperature. This is the temperature scale, and then this is the time axis. Okay. Now, time axis here is logarithmic scale, log. Okay, you can see here 1 second, 10 second, 100 second, 16 minute, and 3 hours. It's not linear scale, it is log scale. Okay. Now, now you see what they do is for making the steel, they pass, when the steel is hot, it's coming out of the rolling mill, they pass it through a pipe with water, okay, or a water bath, very fast. So what happens? It gets quenched, like a blacksmith dips the knife into the water, right, when it is hot, and then he hammers it. So the reason is mainly to make the steel hard, HARD, so that it's easy for so that it is very hard and easy to handle. It will not get deformed and very easily when we handle it in a very rough manner in our construction site. So you need that hardness, and at the same time you need high strength. Okay, you need high strength, and also you need ductility. So there are a lot of things which we have to worry about while making steel rebars, and that is why this beauty of this TMT or QST steel is, so you make this by quenching the rebar, that is passing the rebar through a water bath. So what happens is the surface temperature follows this curve. Okay, so when the moment the bar goes through the water bath, it gets quenched in the water. So the hot steel comes in contact with the cold water for 1 second, and then suddenly it comes out of the water bath, and then the center of the steel is still very hot, the core region is still very hot, right? So that heat also radiates outward, and then it heats the surface again. So that is what we call tempering process. Okay, so you can see the temperature increases again, and eventually it matches with the temperature of the core, which is this curve here. Okay, so this matching happens here. So the surface temperature is different from the core temperature during the manufacturing process. So the surface gets quenched, and then it gets tempered because of the heat coming from the core of the steel bar. So we call it self-tempering. Okay, so that's why the name quenched and self-tempered steel comes from, QST. And ideally speaking, QST is the correct terminology and not the TMT. TMT is the word like Maggie, we say, no? Somebody started calling Maggie, we all call Maggie. But actually the correct name of Maggie is noodle. So like that, if you really think about the technical term, it is QST which is the correct term. So somebody in the early time of introduction of the steel, this type of steel into the market, started calling it thermomechanically treated. And so if you really think, there is no steel which is not thermally or mechanically treated. So all steels are thermally or mechanically treated. So it's really not a correct name, but we have to go with what others say. So we'll also join the same way. But you must remember that it is QST steel. Okay, QST. Now, when during this process, what will happen is, the outer, this is when we quench and self-tempering leads to a microstructure called tempered martensite for the peripheral region, because that surface is the one which gets water, right? Now the core region is cooled in a very slow manner. Okay, now that forms a microstructure called ferrite perlite, FP. Okay, So tempered martensite on the peripheral region and ferrite perlite on the core region. Okay, and this color here is not any Photoshop or anything. This is how you will actually see the bar. If you cut the rebar and then look at with your naked eyes, you will actually see this color difference. With some acid treatment, I'll show you that later, but you can actually see this on all the rebars if they are good TMT bars. Now, what are the advantages of this bar? Low cost, high strength, high ductility. For earthquake resistant regions, you need very ductile rebar. Where is the ductility coming from? It is coming from this part, the ferrite perlite. Ductility, this is strength. Tempered martensite contributes heavily for high strength. Ductility contributes for high ductility. Sorry, the ferrite perlite contributes for the high ductility of the rebar. Okay, so this is essentially a composite rebar. Okay, so if I draw stress strain graph of this ferrite perlite and tempered martensite, I'll see that, maybe something like this, and then something like this, and then this is the TMT bar. So this is for FP, this is for tempered martensite, this is for TMT bar. The center one is like a composite. This is like the composite bar, rebar curve. Okay, so this is for the core region, this is for the peripheral region, and this is for the rebar. So you can see how the core and the peripheral region, the composite structure forming the rebars. Okay, now there are some specifications here. The bars are ideal if 20 to 30% of the rebar cross section area is hardened periphery. Okay, cross section area is the tempered martensite, and not ideal. See, if the dark color region and the gray region, if they are not really uniform, these bars will not behave the way you want it to behave. Okay, so there is a test which is very good test. We call it TM ring test, tempered martensite ring. You can see this bar here. There is a ring. No, you can call this as a ring. So we can call it TM ring test, and this is how a bar will look like. And this is a small test setup. You can see the rebar piece here at the bottom of the photograph, and then there is a camera here, and then you take a photograph. Simple thing, it's nothing very complicated. Okay, anybody can do this in any of the field construction sites. So all you need is a 5% nitrile solution. Nitrile is nitric acid plus ethanol. Nitric acid plus ethanol. And you just make, this is the test. You can see the video. The one on the left side is a poor quality bar. The one on the right side is a good quality rebar. Okay, good quality rebar. And then you can see the one on the left side, you will start seeing that the ring formation is very bad. But on the right side, you can see a full ring formation. You can see here on the left side, it's incomplete, no? But on the right side, you have full ring. Okay, so left side is a bad quality rebar, right side is a good quality rebar. You can very clearly see that ring test. Okay, now these are examples. Again here, this one is a good one, and all these are poor quality. All the three photographs on the right side, they indicate poor quality rebar. And unfortunately, we have a lot of such rebars in the market. What is the problem here is, I have indicated the red dots here. So for example, you look at here, you'll see that region, you have the tempered martensite, which is the dark gray color, ferrite perlite, which is this ferrite perlite, and then this is TM, right? So there is a discontinuity in the ring, okay, or the ring thickness is not uniform. So these are all the problems. Why this is happening is because the steel manufacturers, sometimes they don't quench the steel properly. If the uniform quenching is happening, then you will get a bar like this. The one on the left side, good quality bar with full ring, very good quality, okay, in terms of corrosion resistance also. Now you see here, only the type A is good in this. All others you have incomplete or inappropriate rings, not consistent, not they are sometimes disconnected. You can see everywhere here, they're disconnected, not uniform thickness, so all these problems, in a photograph they might look good, but they're not actually good. They look like flowers, in some cases, but they are not actually good quality rebar. So for a good quality rebar, you need something like this. Full ring is required. And also one more thing to note down is, in this picture itself, if you see, the smaller diameter bar on the top row, 8 mm, is having more problem than the larger diameter bar. So if you ask a manufacturer and do this TMT ring test, they will actually do it on a larger diameter bar, and you may not be able to capture the problem. Because if you want, what you should do is you should test the bar with the same diameter which we are using, not a different diameter. Okay, the ring test should be done on the same diameter rebar, and you should look for the proper ring. If you don't have a proper ring, what will happen is you will have a lot of cracks like this when you bend the bar. And on the site, we always bend the rebars, right? We always have to bend the rebars. And when you bend the rebar, the cracking should not happen. So the picture on the left side is a good quality bar. I put this in a green and this bad is red, right? So a good quality bar, like a proper ring, even if you bend it, there will be no cracks. On the right side, a bad quality rebar, when you bend it, there will be a lot of peeling off of the peripheral region, which is very dangerous for the structure. Okay. And this is, I think, is one of the reasons why we have a lot of the new construction start corroding faster. Because this kind of cracks, if they are happening, you don't need chlorides, nothing. Only water and oxygen is essential. That is all what is required to cause corrosion, because the mechanism of corrosion is called crevice corrosion. Okay. This is what is going to happen if you use this kind of bars. So you must do this TM ring test on all the bars which you get, representative test. Now we bend the bars at the site, and then while bending, this kind of crack should not happen. Why do we use this bar? We use this bar for getting ductile performance for our structures. That is why we use TMT bars. The core region is more ductile, I told you, ferrite perlite is more ductile. The peripheral region gives you the strength, which is tempered martensite. So the ductility is the key thing here. And for achieving ductility, we always bend these bars by 135 degrees. Okay, 135 degrees. So when you bend it like that, the bar should not crack. Okay, so like I showed in the previous picture, if you bend it like this, bar will not crack if the ring is proper. If the ring is inadequate, it will crack. Now, another type of rebar is corrosion resistant steel, which is actually essentially by addition of a little bit of copper and chromium and a little more phosphorus. Okay, so these are the three additional ingredients for the steel, and then you get this rebar called corrosion resistant steel. Okay, and here one important thing I would like to mention is that test the chloride threshold of this steel, because if you look at the durability or service life of the structures, it is the chloride threshold which is more important than corrosion rate. Why I am saying this is, most manufacturers, when they sell this corrosion resistant steel, they will say that corrosion rate is low. But that's not the key parameter to look at when we look at long service life of the structures. There is a more important parameter which is chloride threshold, or even pH threshold if you look at carbonation. So chloride threshold is the parameter which you should look at. What is chloride threshold? It is the minimum amount of chloride which is required to cause corrosion. Okay. We'll just leave it at that level. Okay, you don't need to go too detailed. Now, stainless steel is another type of rebar which is also getting more and more popularity. What is stainless steel? 11% of chromium plus nickel and molybdenum. If they have, then we kind of call it stainless steel. Now, passive film is the main oxide layer, mainly chromium oxide. Okay, passive film of stainless steel has chromium oxide because you have a lot of chromium present in the stainless steel. Now, this picture below, this is an example photograph of stainless steel. Looks shiny, bright gray color. So picture on the bottom line will tell you very clearly how important or how good or useful is the stainless steel. You can see these pillars here. Okay, they actually belong to a bridge which was constructed after the bridge on the right side. So, corroded piers with black steel. Black steel is the conventional steel rebar. Okay, so these piers are all corroded, and then, but this bridge was constructed after 30 years later than those on the right. This is a bridge with stainless steel rebar. So, same marine environment or chloride rich seawater environment, you have when you use stainless steel, it does not corrode. So it has very high chloride threshold than the regular steel. What is chloride threshold? It's the amount of chloride which is required to initiate corrosion of the steel. For stainless steel, you need much more chlorides than the regular steel. Okay, so let me write that terminology here. Chloride threshold is very high for SS or stainless steel. Okay. Okay. Now, they are what are stainless steel? They are alloys that contain at least 12% of chromium. Other alloys such as nickel and molybdenum are also present. And passive film, essentially, it has a significant quantity of chromium oxide in that. That provides the corrosion resistance. But cost is a little bit higher, 6 to 7 times more than typical steel. So, but we have to see, it's not the capital which is we have to worry about. We have to think about the life cycle cost. So, if you want a very long service life for the structure, and in aggressive environment, probably stainless steel is the way to go for. Okay, but you have to see, you have to do this cost analysis, life cycle cost analysis, and then only you have to make that choice. And also when we saw, there are some cases where people say you can use some portion for stainless steel and some other portion for other normal steel. Okay, or the more vulnerable locations in a structure, like the very near to the surface of the concrete, you can use stainless steel, something like that. So in that case, we have to look for something called galvanic corrosion. Okay, galvanic corrosion is nothing but when you put two metals together, one metal will corrode in preference to the other or before the other. Okay, when they are in direct contact. Okay, you at home also you might see this. Sometimes you will see that in door hinges, etc. You will have a metal which is stainless steel and then screw will be mild steel. So what will happen, or the other way? So two different metals are used. What will happen is at that intersection, if you look carefully, you will see that there is some corrosion happening, and that is because of the contact between the two metals. Okay, so when two metals come in contact, two dissimilar metals come in contact, then there will be a battery will form, and that will cause the galvanic corrosion. So when you put stainless steel in combination with the other steel, you must check whether there will be galvanic corrosion or not. That's something important to check. These are some examples where stainless steel rebars have been used for bridge construction. Okay, but in India we are still not much, because this is in Toronto and New Jersey, very cold climate where they have severe chloride. They spray chloride onto the road surface so that you can drive during the winter. Otherwise, there will be scales of ice will form on the road surface and you won't be able to drive your vehicles. So they have a lot of de-icing salts. They spray chloride solution onto the road surface to melt the ice so that vehicles can drive. But unfortunately, we don't have that problem in most part of our country. So we have to still see where we need the what are the type of structures where we will require stainless steel rebars to be used. Okay. Now, to summarize today's thing, we looked at a history of steel rebars, and then we also talked about the plain and ribbed rebars, then CTD rebars, and then TMT and QST steel rebars, then corrosion resistant steel and stainless steel.